Okay, so we started the workshop, right? People can join.
Yep, it looks like people are joining now.
I should record it. Okay, waiting for people to join. Hi everyone, this is ATM Cyber's reverse engineering workshop, and we'll first start this is the event checking code. If everyone can see it, just please tell me if there's a problem. And reverse. Wait, why you do just typing that into the membership portal. Yeah, plenty of time. So I think everyone has done that. I will see. If you haven't done so, let's just type in the chat and then I'll see. Okay. Move on to the next slide. So first, who am I? I'm a first year undeclared Stephens College leader, or V1 you can do computer science. And I like I'm probably the very few ones are good at reverse engineering in ATM Cyber. And I also really like system programming. Uh, uh, like system programming is like C, Rust, Go, and other languages. Is the characteristics is that it's close to the metal, close to the machine, and I really like those type of things. And I'm quite good at assembly, even though some people hated it. This workshop will not cover anything that's require assembly or any of those weird stuff. You you can just know Python and C and pretty much good to go for this and very intro level workshop. And my favorite is CTF category. If you have gone to this capture the flag workshop, as the UIU CTF 2020 kernel exploitation, that category, the series. And yeah, and I got almost every challenge except for the last one, just run as root. And most of them is about assembly and stuff, but in this workshop, we will not cover anything assembly. Okay, that's right here. That's myself, and it's continued going. So, so I will launch a poll, and just note that there will be a multiple choice poll. So make sure you select all the apply. I will launch it soon. Okay. So yeah, can you guys see the poll? Okay. Make sure you select all the apply. Okay, I'll just wait for half a minute and we'll close the poll. Wow, it seems actually there's more people that know assembly than I expected, which is good. You'll probably find reverse engineering to be very useful, helpful there. Okay, I'll just end the poll. So yeah, so most people are familiar with Python, and actually half of you are familiar with C, and yeah, most of you know Java probably because C is 11. Yeah, but regardless of what you know, C is mostly like Java. It's almost very similar, except there's some tricks and stuff, but you don't have to deal with that if you're using a decompiler. Ghidra does most of the job for you. Okay. Let's share the result. Yeah, and that's the result. Okay, let's move on to the next one. Next slide. So first, what is reverse engineering after all? We haven't even answered this question yet. So reverse engineering by its name is called reverse engineering. So it's the opposite process of like going forward. We will call forward engineering, which is actually writing code in a high level language like C, and then compiling the code into a lower level language, assembly, and running it. So in this, so actually reverse engineering takes many forms. It can be anything as the reverse of engineering literally. Uh, for example, if you are reverse engineering can be done on like physical machines, like in addition to like software and hardware and stuff. Yeah, there could be hardware reverse engineering, but here we're only focused on software reverse engineering. That's usually it's so software engineering is turning code into compiled binary and running it, testing it. And we're doing the opposite. We we have only the result of the code execution. For example, we have the binary image, which is this binary is just something you download, for example, exe file and those of sorts. Even though it seems like it's a black box, you can't see what's inside the exe file. But if you open it up using a hex editor, you will see something like on the left side of the page, which is like 55, 48, and all those hex digits. It seems like such a pain to read those, but with the aid of like some decompiler, you can easily turn that into at least something that's very similar to the right side, where is a C code and something. Yeah, and in addition, you may have access to other stuff like debugger, maybe even the memory of the process, but you have everything except probably the source code and like how it works and stuff. So our goal is go from the left to the right. And it's not going to be pretty hard. You don't have to read that yourself. You can utilize tools such as Ghidra, which is like the main focus of this, and also Radar 2 and the stuff. Yeah. Uh, yeah. So first, why reverse engineering? Yeah. To reverse engineering, like can be used by bad people, like just illegal people to like try to crack software, but it can also be used for like by good people, not just bad people. Just to remove, for example, you want to ensure interoperability with another software. Maybe you want to run, for example, run your own game on a machine that's only locked down to a store. Uh, or yeah, basically, if you can reverse engineer, for example, like Wine, which is a compatibility layer, it allows you to run like PC games, which is for Windows on like Linux machines, which like makes Linux gaming quite popular this way. And Wine is a project is mostly done through reverse engineering of the Windows API. And of course, it's a legal form of reverse engineering, and it's producing the binaries and yeah, so it reverse engineer the Windows API, and then the like apps that run on Windows also run on Linux because of Wine. So and also reverse engineering is just for fun. For example, it's kind of like reverse engineering is a lot like puzzle solving, except it's a quite harder puzzle. But I find it very interesting, and you guys will probably like find it like interesting at some point. Once you know just once you like is able to enter the field of reverse engineering, I think the biggest barrier is just the barrier to entry. Like even go into the field, you might get scared about all those like binaries and stuff. Hopefully, this workshop will make it very easy for you. Okay. So here you will find the first challenge of the thing. It's not going to be hard at all. It should be like easy. It's not that hard, but it do requires a lot kind of the thought, a good thought process. So, and I will like give you hints and other stuff if you need. So basically, you could just go to this ACM URL/reverse, and it will go. You will then go to directly to a Google Drive folder where you can download all the binaries. So all you need to do is download crackme1.py, and yeah, and I can also send that in the chat you need it. Yeah, just do like demo, give a quick demo of it. I will go to the website and I will go to this link and show you what's like in there. So here you go to your folder and download one of the stuff. It's a Python script, so you don't need a Linux machine to do that. You just run it on your own. So crackme1.py here. Yeah, just download this and try to see if you can get the right input. So here I will run it on my own machines and like just demonstrate it if you can do it on your end. So let me find it. Yeah, here's this Python script. Yeah, you should be able to see the source code right, like on my machine. So I will try run this Python 3 crack v1.py. Make it slightly bigger. So it's easier to see that the input the product key to unlock this program. Oh, I'm just going to type some random one. It's the invalid key. Get out of here, right? Cracker. Giving you random input is unlikely to work, and it probably won't even show an exception because the code is quite well written. But the key is you go to the source. Since you have the source, it's easier. So go down, and the code execution starts from here, and as runs main, input the product key to unlock, and here input, and it returns the key to key and split it into C parts. So here I need to know the structure. It's like ABC, like BF, like 0, like that. It's going to be 3 parts, and the first part, first you check to the component, 3, which is like 3 parts ABC, BF, like bunch of zeros. The first part, so and this should be quite easy to figure out, I suppose. This line reverses the first component. For example, it's ABC, it becomes CGA, and checks that if the component is this kind of like gibberish. See if we can figure out the first part. So one way to check that the first part succeeded, but not the later ones, is to do something like this. Comment out the second 2 lines and to comment out lines. So and run it again. For example, if you give random input, it still can work. But yeah, can anyone figure out the answer to the first part? Maybe type it in the chat. So I know that you guys are working on here. It's okay to publicly chat me about what do you think the first one's going to be? The first component. Yeah, good job. If I type reverse and something else, the product successfully activated, woohoo, but we modified the program. So to actually activate that, we'll need the second part and the third part eventually. So yeah, the commenting out is a very good strategy in Python. Since you can modify the source code in any way very easily. Let's see the second part. And this and this. And here. Now it has first part, and the second part, and reverse by itself won't work. And you need the second part. So here, just not sure how you're familiar with Python, but hex function it returns a hexadecimal representation of it's not accurate. It's supposed to be a byte, and like I said, like if they give you a byte information, byte is like a string, but in Python 3, there's a difference I will tell you like later on. Just consider that as a string for now. And hex, it will give you the hex representation of the one. And actually, our like Discord bot NSA has a way to do this too. It's just a Python way of doing this. It converts character A into 61 and B into 62. For example, it's an ASCII code and it's in hex, so it's actually 0x62, which is another decimal number. And here, so there's an encrypt function, and here's what the encrypt function do. So can you guys guess what this function does? Think of the byte returns an iterable, which a list should be something you can iterate over one by one, and the list is made with this comprehension. Yeah, not sure how you guys are familiar with these comprehensions, but this is basically iterating over like the thing you want to encrypt with character by character, and this does something with the character, and it returns a byte, which is by concatenating the characters together after encrypting them with this operation. So I guess what this does in Python. Maybe type in the chat. Yeah. Yeah. Okay. I'm gonna get started. Yeah, it's XOR, exclusive OR, exactly. And so overall, this thing runs exclusive OR on every single character, and I can actually put it in the prompt and see how that encrypts stuff. Encrypt. I will try encrypt. Yeah, you have to encrypt a byte. So B A DF DF DF. See, that's encrypted with each letter with DE. The ASCII representation of A is 61, and with B C hex. Let's do SDF, and if ABC, then it gets to BCC. So yeah, not a very strong encryption indeed, because all you can just brute force 256 combination, but that's about for crypto, not for this thing. So yeah, it does encryption by encrypting each character by the explicit. And one feature of XOR, I think you kind of need to use here is that remember that XOR is I'm not sure how you say that, but kind of like commutative, but yeah, it can be undone using the same thing. Like for example, 0x34 XOR 0C. If you want to decrypt it, do the opposite thing. You just XOR with that again, and it should give you back to the same result. Yeah, XOR. So you run XOR twice, and it gets back to the same thing. So this is a very useful way to exploit this here. So we encrypt what you do with hex and encrypt it and becomes that. So what do you guys think which I should do to decrypt this hex string here? Yeah, it's just XOR again. So I'm going to get the encrypt function in there, and first I have to like unhex it, kind of like there is a way to do that. It's bytes from hex. Let's do this. Let me get this byte and I encrypt it again. Oh, I think I get something. My live please, it says, and I will run this again with the second part added. Product successfully activated again. So we now get the second part. So the third part is a bit of math. But don't be scared. There's actually a lot of ways of doing this. Some may require a bit of math, but most of them doesn't. Like it's not a lot of math. You can even brute force using some Python code anyway. I just review one of the ways to solve this. So the last part is check-ins, the second one. So yeah, this is just kind of like error-free way of checking in because you don't want errors to pop up, and so you kind of know what this thing is doing. It's kind of the reverse engineering. It's want to hide the program, obfuscate it, making the error message as like least user-friendly as possible here. And it's eventually basically just turns into an integer and run some math on it. So x minus 3 times x plus 7 is this number. So maybe give a guess of what this number should be given the magnitude of this. This is 7 digits as that number. And hint, it's somewhere on my screen right now. To tell you. And my mouse is quite close to that. You can perform the calculation yourself in Python, for example. We try, for example, 2 numbers. This is obviously not the right one, but we're just telling you how to like calculate it very easily. You can even make x. And yeah, there are obviously about a lot of ways you can script it out. And can anyone give a guess of what this number is probably is? Yeah, just take your time and I will be waiting there in the chat. Yeah, that's the equation. Well, oh, so are you saying that that's a string? Meaning that this thing, I'll just say that except an integer. Yeah. Yeah. What you mean is like solving this thing. Yeah. Like you're encouraged to use any online tool you wish to solve that. Because in CTF, you're not restricted to, it's not like tests or exams. You can just use the entire internet to do whatever you want. So everything is fair game here. So, and there's, yeah. One of the ways to do it is to solve the equation. But there's more than one way, of course. And just be careful that this thing, because it's splitting by the like dash, and dash is also for the negative sign, the number cannot be negative itself. It's going to be choked by this. It's going to be the split. I think this uses split numbers is a negative sign, so it has to be positive. Yeah. Feel free to type it into chat and let everyone know what it is. So that's kind of obvious. And once you know it, it's obvious. Yeah, good job. 2020. It's just yeah. So it's more on my screen really, on my calendar, and it's part of my own screen. So okay. So here I will try get the entire thing done. Okay, product successfully activated. So this is the product key. We cracked the first program. Where's my life, please? 2020. So now I'll go on to the later one. So you can now get a gist of what reverse engineering is like. So CTF challenges will ask you to like give the correct input to your program, so that will demonstrate that you can actually solve this thing. So yeah, you actually know what this program does, and that's one of the ways for CTF challenges to like let you demonstrate your knowledge of the binary. There are other ways, like for example, optimization and stuff, but we won't go over any of them in this workshop. Okay, I'll go to the next slide. So here, what if you don't have the source code? Or what do you do now? Like, if you don't have the source code. So first, you need to understand like how a C or C++ programs compile under the hood. The same thing should apply for Java and all the other stuff. It's just maybe a slightly different process, but almost all programming languages that is compiled. Actually, even Python do it. Even C Python do bytecode things, but I will discuss that later on. So here is this source code, and see it have RC, RV, and seeing all those comparisons and opening a file. And if it fails, it prints an error. And turning that into assembly. If you're a good assembly, you may see a correspondence. Especially here, it's a call open. You have a call open here, which corresponds to the open function here. And JNE is a branching. It's using this FD check, taking over with -1. Yeah, X is -1. Yeah. So yeah, and you kind of see the correspondence, but in machine code, you can really see no pattern here, even though it's really like corresponding to the method. For example, like you see 5548, that means the start of the method. It's actually being pushing the string pointer, but you don't need to know that. It indicates as a start of the method here. And so a C program is usually compiled using first the preprocessor and then the compiler, and then when it goes into assembly, and then it uses the assembler and the linker to put it into machine code. And going in reverse, so how the program is decompiled. It's clear. Okay, and how it's going to decompile. So here you start with the machine. The only thing you have, like as a reverse engineer, is that you only have the machine code, but you don't have anything else. And that's kind of a problem because you can only run the code, but not see what is actually happening, at least not directly. And hopefully, like fortunately, we have tools to help you go from machine code to at least a more readable form, and that is a disassembler. So disassembler, for example, Radar 2 and the non-pro version IDA also does it. Those give you assembly output, but as I said, like assembly is quite hard to read, and you're not even required to be able to read assembly or anything in this workshop. But so and for reverse engineering, even for like advanced like reverse engineering, it's easy to see it in the source code form, which requires some other software. And can you guys guess what this question mark here is? What's in the name of this workshop? Yeah, Ghidra. Okay, so we'll go to the next. Here comes the Ghidra. Ghidra is finally a decompiler, which turns the machine code binary all the way from its binary form to back to its source code form, and doing the best it can do to like reconstruct it. So if you know assembly well, then you will know that every issue you don't even need to know like assembly, and you will know that like it's not possible to make perfect decompilation. Yeah, and hello Tristan. And it's not possible to make a perfect decompiler because obviously you will lose things like the comments, because the comments have no use and get deleted by the compiler before it gets compiled. But it finds patterns in the code, so it's actually quite smart. It knows that maybe the code is compiled in GCC, so it uses its pattern to like decompile code even better. So you may have downloaded this before, but if you haven't, go to ghidra-sre.org. I will send the link into the chat. Ghidra is, yeah, and download it from there. And I'll just wait for I guess a couple of seconds, for minutes, maybe a couple of seconds, maybe for people to download Ghidra before we move on to the next one. And at the same time, I will show you like the interface of Ghidra and kind of the basic thing. Yeah. So Ghidra. Okay, I'll open this. So here's the Ghidra. So, I have the here it is Ghidra. Ghidra is an thinking project, so you have to do a new project, a non-shared project, and go through stuff. See who's in the chat. Oh yeah, what do you need to run? So I guess the name of the thing is should be like a shell script. For example, in Windows, it's batch file, so BAT batch. It's called the batch file, and it should be named Ghidra run if I remember it correctly. So yeah, run Ghidra run. The other file is for Macs, I think. For Linux, you do this file which is a shell script. In Windows, just double click the Ghidra run.bat, and it should open up. Yeah, you basically want to do a new project, type a name and finish, and it will create, for example, something, and it will create a project for you. I already created one. Just tell me if you have any trouble doing that. It shouldn't take you too long to do that. And make sure you check non-shared project. Yeah, first thing you need to do is to import the file. So yeah, so I haven't told you. So yeah, first you have tell you the binary you need to you need to download it from. So it's called starter. In the same folder did before, download this binary. And after downloading it, these are like you import file and find the file, and yeah, and it will walk you through the process as well. So yeah, using these ones. Wherever you download it, you should first go to file, import. I'll find the file. Start it. Yeah, this yeah, and download it, starter, and open it up. And this binary is not from any CTF challenge. It's one made by myself. Okay. Let's click OK and ignore all that and double click to start. When you first open it, it will tell you whether you want to analyze this. Choose yes. Usually for smaller binaries like this one, you can just analyze everything, and it shouldn't take too long to do that. Yeah, after you finish everything, you can click. Yeah, your interface may look a bit different because I have all those settings set up, but you should have a decompiler on the right and a assembly listing on the middle, and on the left, this one is what we are quite interested in, like for symbol tree. Then click the plus on like functions, and you will get a list of symbols. So here it seems that main is not there. I can actually confirm that. As you go to, just press the keyboard G, and it should bring up this go to thing. I can literally go to anything. For example, main. Here it said main is not found. That's because usually the CTF challenges, they strip all the symbols, and I did it too. It's basically main meaning you won't know the function names and all the stuff. So the function will kind of give it random names. In reality, they're not giving any names at all. It's the Ghidra who actually finds who detects function and do it. So, but what we can do is there's always an entry point, and the color is different to symbolize that it's not a regular function. It's the entry point of the entire program, which means that every program within any language, even assembly, will start here. like for example, assembly programs don't have main, so they will just start here. And which is the entry point, it can always be determined from the binary, assuming it's not like corrupt or anything. So yeah, the entry function. Yeah, something interesting happens there. So if you're just coding in C, and you won't be able to see this low-level function called live C start main. So this function just runs the main function, given and it does that by like require you to give a pointer to the main function. A pointer is kind of like a reference to your function. If you know in Java, you have references, and like so giving a reference allows you to call this function. So you see it's a pointer. So the first pointer is the pointer to main. It seems that this name that isn't main, but it's actually the name Ghidra gives it. It's a blob of code that Ghidra does. I think it's a function. You can always rename it by right click. Okay, I'll just go to that first. Double click this in, so you can go to that. And here, oh, that seems like more like the main function. And now rename function, which can also do by pressing L. Let's call it main. So here now you have a main function here. Ignore the first line because that's retrieving a canary. This is a security feature. We won't go over in this. Enter the secret or letter. Yeah, I can actually give you like an example interaction. That's the first thing the binary should print. So here, louder. Enter the secret flag. Let's see. This is not the flag. This is not the flag. That's how the interaction goes. And let's give it the right flag. Yeah, it's running an fget. Fget is just reading characters from standard input, the function you see, into a buffer, which is here. So here again, I will rename this buffer as input buffer to make it name better. And here, also note that the variables are not named correctly, because also the names are also stripped from the binary when you compile it. And the only thing you don't know again is its address. Like there's a list of local variables here based on where they're located on the stack, but they don't have names. So we need to give them. So if you need more readability, for example, like you can read this, but it's just harder, especially for beginners. So I recommend you like rename all your variables. Do the same thing. I will rename this length. Yeah. Oh, you actually get the first part. So hover over this thing and it will translate that to decimal. So if the length is not 35 characters, it will just print this is not the flag right away and not proceed with anything. So at least for now, we know the length of the flag, which is 35. And here, this part may seem like quite difficult, but I will decipher like to decode what is going on here. It's a while loop. So Ghidra usually doesn't translate for loops very well. Only do while loops. This should be a for loop here. You can rename that to I, the loop counter. So when I is less than the flag length. Actually, yeah, the flag, you can see the string also has a terminator. So that's why there's like it's 35, including the null terminator. And as it reads the input, it turns out the character and here, we wonder what this function does. It's another function in the file that's unnamed. And okay, so seeing this description of a function, like ignore its name. What do you guys think this function does? And this function, yeah, this function should be quite easy to understand. If you know anything about Java or C, you should really guess what this function does. And here it is calling itself, so it's recursive. what is this function doing? Type the types are in the chat. Yeah, the Fibonacci sequence. So so here, because it's the recursive case, is that we will call the previous two functions with number -1 and -2, is the two previous terms. And when it's less than 1, it's just print this up with the zeroth element of Fibonacci series is 0, and the first one is 1. And the later ones are just the sum of the previous two terms. So I'll rename this using L, then I'll use the shortcut now, and Fibo, and for Fibonacci sequence. And let's go back to main. So just press the keyboard G. It's a shortcut to just type any name of the function and go to there. So now I'm back in main again. You can always go on the left symbol tree and find the functions here. Go back. I think even go back, but yeah, go to previous location. And you also use that. Many ways to do it. Yeah, it's computing the Fibonacci sequence of the index and multiplying that by 29. And there's kind of operator precedence mess here. Yeah, the thing I hate about Ghidra is doesn't do the parentheses, but you should know that the multiplication should go before the XOR, exclusive OR here. So multiply by 29, exclusive OR by the Fibonacci number, and added by C. Eventually, it should be this thing. If it's not, you see, if it's not, then this will this thing will become true. Yeah, this flag that you check that we'll just rename it that. If that is true, now there's no way to revert this thing, but it's or when that, and it has to remain false at all times, because otherwise, if it's true, then it's going to be true at every round, and it's going to print, and this is not the flag. So it has to be, that means that it has to equal to this index I of this thing. This thing is a blob of bytes. If you double click into it, it seems like gibberish here, but it actually is some bytes. It's not printable, but it's some bytes it used to validate the input. So the first character after applying this mess will become hexadecimal 66. Second character after applying this will become 88. This is a slightly more difficult one, but you can use that to reverse and get back to the flag, because all of these actions you see are reversible. You can subtract by C, so subtract 0x66 by C, and XOR by the Fibonacci number, and eventually, like, we want to reverse this multiplication. Okay, you don't need to. It's just subtracted by this, and it should be fine. This can be quite easily automated using a Python script, which is a common technique in reverse engineering. I will present my solve script for this. So yeah. So here is my solver. So let's see. It reverses the step by first showing the encrypted one. You see, this sequence is what I just copied from Ghidra. This is 6688 9A BC. I put that into Python, and Python as a byte string. This one-liner is kind of messy, but it's doing the time. I can rewrite that into a better for loop. So yeah, of course. It's going to encrypt this in. The first thing you do is XOR by. I also implemented Fibonacci sequencing, the better implementation. XOR with Fibonacci I. Then the second thing it does is subtract by 29 times I. And at every step, I added this so that it remains in a single character, like a an 8-bit integer. So it's technically not 256 at every step. And if you run that, magic will occur, and you will be able to see the flag. Okay, so decrypted, and this all is decrypted. Let's pump up again, get excited. Let's validate that that's actually the flag. Oh, you caught me, and that's the flag. Oh, great! That's the first binary we managed to like crack. Okay, and I will move on to the next one. So now, after this, we will discuss like tactics of reverse engineering, just strategies we can use. So the first one is, I guess the workshop starts getting fun after this class. We'll be using many tools to help us reverse the thing. So the first one is GDB, which is from the GNU debugger, and there's also debugger is a very useful tool for reverse engineering because first it allows you to like view the memory of the process while it's running. Like, but usually memory is something that the program is private to the program, it's not visible by any other program. But our computers, for debugging purposes, the computers now all have like debugging functions, which allows you to like, which allows you to see the memory of a process, and that's useful for debugging like low-level programs such as C. Because C is technically compiled, not like interpreted on a virtual machine. So to view it, you have to be able to view the memory. And for example, Linux does it through ptrace. And GDB is a very useful front end, and it's a command line debugger. So it's not like in Visual Studio Code where you have like run the F5 to debug. It does everything on a command line. And since you don't have the source code, maybe that's the only way to do it. Maybe there's other ways. And like, for example, like all the debugger, which is like this, but usually it's for Windows as far as I know. And there's also other options right there too. We'll focus only on GDB. I see like this is just demonstration. I see you can like for example, you see it must be safe, right? It's in the memory. Yeah. So also another thing is that don't assume that like when you are writing software as a company, don't just assume that the user is never going to know anything in your memory, because they can always run a debugger on you. How you deal with that, like or even allow this is depending on your policy, but don't put any like cryptographic keys or passwords like into your memory for a long time, especially those like they're supposed to be secret. And that's actually how some DVD like players got their keys hacked, because every user who can like entrusted user can like have a copy of the DVD like player, also have a copy of the key that's running inside the memory. The key may be like quite encrypted on disk, but in memory, it has to get the key somewhere in the memory to like decrypt the music or video or stuff for you. So, and if you can get the keys and just play those DVDs without copy protection, and that's how people is able to like craft the DVDs. So yeah, so we'll just without saying anything like it, so we'll just get our feet into the water. GDB 101. So this one we're taking a break from reverse engineering to kind of like more like forward or software engineering. So there is a bug in the buggy.c, which you can also download from the list. In the same folder you download the binaries, buggy.c, and download it and see if you can find a bug in the C. not pretty obvious in the bug what it is, but if you know programming, you should be able to know what the bug is, even though it could be quite difficult. So yeah, I will show the source code, and you guys can see whether there's a bug. Yeah, just opening it up. Yeah, on my computer, it can show that it's a program that reverses an integer array. It seems that everything is working as a reverse function, print array, and main, which is, and let's run this code first. Run this code to see what bug it has. Ultimate array reverser. Reversing an array in a live store is going to maybe not sure if you guys can see the pun here, reversing your array. Yeah, let's into a list of integers and see if we can reverse it. Well, before reversing after, it doesn't do anything here. Oh, that's we see able to first we get the first step, which is to reproduce the bug, and you can see that any array that's not palindromic, it can be exhibit this bug, which means that it doesn't really reverse the array at all, and it's not just related, yeah, anything or anything is literally. So, so I'm not sure if you guys can see the bug. Yeah, to make it like more friendly to like people who don't know C, I'll focus the bug on the first page, which is here. It's not anywhere underneath. It's just on this page I'm showing right now, the bug. Yeah, I'm not sure if you can see the bug. But if not, the purpose of debugging is to find the bug, not by inspecting it, actually running it. So I will leave that as an exercise to yourself. We will start trying to find the bugs by running a debugger on it. Okay. So first, you may realize that we compile the binary using the G flag, which the G, which enables debug information for GDB to know it. That's the command line gcc -c-o. And that gives you some debug information. For example, the variables, you can just manipulate them directly, and other stuff. And this is a very good tool. So like that, first I would just show the conventional GDB. Okay, I'll be back and I'll run GDB. Again, you just need to type the program name, not anything, not the C source code. Anything stuck, and it will spin up GDB. So you are met with the first prompt is parentheses GDB, and it's like the command prompt where you get a type command, and you type help and get all the help and stuff. I will give you a cheat sheet of the stuff you usually know. So the first thing you do is at every GDB prompt. So if you don't need to run the program with any arguments, you just use a run command here. Oh yeah, I think you guys already found the bug, but I will demonstrate the bug by actually debugging the program. So the first thing is a run program, which you can either use a full name, which is run, or just R. Both of them are equivalent. I will use a full name, run, and it will start the program. As usual, ask you for a list of integers. And it exits after runs. So it doesn't seem it's different from using the shell, running on the shell. But what you can do is that before running, you can set some breakpoints, which is the point you want to stop the binary, like it's the point you want to stop the program. for example, people pointing out the bug is in reverse, and so an educator gets whoopee there because the printing is all okay before reversing, after reversing. And I actually hinted at this actually in the function. So how do you set a breakpoint when the program calls reverse? So to set a breakpoint is at line 15. So let's say break 15. Let's see. Here, there's also an address. This will be important later on when we like debug the binary that doesn't have the source code given to you, which is what usually CTF challenges ask. You need to break at those addresses. I will tell you later on how to identify which addresses, but for now we'll do the easier way, which is just type a line number and line 15, which is the reverse, and after that, just type run and 1, 2, 3, 4, and yeah, see, GDB stops here and asks you like to enter a command now, which means that it stops the program here. And precisely as this line, actually line 16, which is the entry of the for loop. And so how do you go step over this line? So stepping over is, so there is next or step. Here is your equivalent. But if you're calling a function, next skips over it, but step gets into it. If you know debugging, you should know the difference. But here, we'll just use next. Okay, so if you next to go to the next line, let's say it's going to the 10th in the array. So another useful feature, I don't think it's listed on not on the cheat sheet, is that you can print stuff. You can use print array and print the content of the array. Yeah, here the array is oversized, so the array size is much greater than the input. But so we are only interested in the first few ones, like 1, 2, 3, 4. The other ones should all be 0. And GDB does it very smartly because it's seeing all zeros. It's only saying repeating how many times. It won't spam your console with the entire stuff. And as you can see, you can also print other variables such as I, which is it's on the first iteration right now. You press next again. And the temp should change to 1. Yeah. It's performing a swap, and you can skip over the swap. And now let's print the array again after the first iteration. 4, 2, 3, 1. Swapping the first and the last. I will just do 3 consecutive next again. Array again. Yeah. I haven't done just because everything. Yeah. 4, 3, 2, 1. Oh, now it seems like it's actually reversed. So why is there still a bug? Next, LC that. It's not exiting, and it's going another iteration, and it's back again. So if you exit this thing, you'll see that array eventually the 4 will be exchanged with 1. It will end up with 1, 2, 3, 4 again. So that's a bug here. You just discovered the GDB, and you can get out of this function with fin. So it gets you back to main. And also another thing is continue, which also by the way, fin is just to finish this function, like get out of this, which is like stepping out. You know what the step out mean? Debugging, and you're back in main. So GDB can also continue, or maybe previous you see, which continues running and exited normally again. So so to fix this bug, you just have to change this to over to it only does only stops in half of the thing, and it's enough. And it can be proven that like regardless of whether it's odd or even, it will work. So recompile it. And buggy. Compile that again. No longer buggy now. It successfully reversed it. So, woohoo! we made some program work in GDB. So that's just a primer. We'll get into more serious debugging with like only binaries. Yeah, in the next few slides. So now download debug me, which is binary in the same folder, and see if you can run get the flag. So I will go over this one too, because this is going to be a bit challenging. But a good exercise would be to try to run GDB on the binary, so GDB debug me, and see what's different from this one. If you have downloaded GDB, you should be pretty obvious, especially if you run next or step or even set breakpoints. Because now you don't have a source code, so GDB just see what will happen when you run GDB and you set breakpoints and other stuff. So I will demonstrate on my side. Let's run GDB. Let's first just try running the binary once. Always good to run it once. And what am I hiding? Yeah, this is not what it is hiding. Nothing. So get this brute force. We now use GDB to figure out what's going on under the hood. Also, first, the first thing to do actually is to also to open it up in Ghidra. Yeah, you can try that. But eventually, what you will notice is that this could be too complex for Ghidra to analyze, or at least too complex to implement the computations that's going on underneath. I will show it regardless. Debug me. Analyze this. Entry. Let's put entry again. Rename this. Go to the function. Rename this to main. Yeah, I think that is feeding a random number generator with the speed lead cafe. Oh, yeah. If you're interested, you may be able to at least get what's going on here. Yeah, here is this one is not Fibonacci but Lucas sequence. Continue another sequence. Even those complex stuff going on in the back, I'm not even want to see what's going on there. It seems like it's using some very random function, but let's see what eventually end up in this binary. The global binary. This seems to be some sort of buffer. Let's see. This function, what it is doing? Oh, this is the part where it's checking the flag. So yeah, so say what am I hiding? And read some input into this input buffer, and yeah, this thing again, you see the similar pattern we did before. This is an equal function, but it's not just equal; it's timing space equal. It's a special one that's because it doesn't terminate early. For example, using the break statement to break out of the loop. It doesn't break out of the loop early, and instead use the OR operation at the end. So that this is a way to prevent people from using timing attacks on this binary. But if you run it fast enough, many times, there will be a noticeable difference in how long it processes a long string versus a string that has more correct letters than a string that doesn't. Because it breaks out of the early means that the first character is wrong, you know it, and you will just try until the first character is right. There's a we could automate it, but this prevents it. Let's think of it as a regular equal function. So it's checking the time is equal. Oh yeah. Second one is something to compare it against. Yeah, the input buffer is compared against this. This is the length for 36 characters. comparing to Ghidra gives you an extra one, but this one should not be there. Sometimes Ghidra does that. When it returns 0, it means it's still not equal, and say take a billion years to figure this out. Not because it's so complex that this thing you compare against, this is computed from many procedures we've seen before. Everything you made before was just to compute the content of this buffer, and so we can write a script technically to do it, but it's going to be pretty darn difficult to do. So what's an easier way? Like, since it's only comparing these two things that are equal, how do I know what's the correct input? So the correct input is just in compare against. It's hard to compute that thing. But if we have a debugger, if we can print the variable in this buffer, we'll be able to get what the fact should be. And so I'll run GDB. So here, it is very different from the normal one, because if you try to run break, for example, 14, it says no symbol table loaded. It doesn't have a source code associated with it. I have it on my end, but you guys won't have it. So let's just work it out. So instead of setting breakpoint as line numbers, the equivalent of line numbers in assembly or binary form is the address, just address of code. Each instruction, assembly instruction, has an address. This address is due to the machine has an instruction pointer that contains the address of the first code that's executing, and it changes the address to the next one after it executes this. So it is line numbers in C. So my bet is to say I want to set a breakpoint as right before the timing state equal, so I can get the exact content of compare against. So I'll copy this and put that into this and see if it works. Yeah. Okay. Now you guys will see whether this works or not. After setting breakpoint, I will run it. You see, I cannot insert breakpoint and I cannot set an address. And this is because GDB apparently my binary is compiled with this position independent code, which is basically instead of loading the binary address 0, which then the address will be easy. There's an offset there's some offset to randomize each time it's run, and so that it is used to protect against vulnerabilities, for example, in binary exploitation challenges. This is a very good strategy to prevent people from hacking the binary. And to make it easy, I shouldn't even do that, but unfortunately, in CTF challenges, they do that all the time. And actually, the GDB actually make it easier by actually disabling the feature of address space layout randomization. Disable randomization, so each time it runs the binary, it loads it at the exact same address, and the address is going to be the same every time. But the downside is it doesn't just load it at 0, and loads it at some random address that's not known to you beforehand. So how to figure this out? It may depend on your machine, what this address is exactly going to be, but we can always get it by running a binary. So let's restart by rerunning the binary. Run it without any breakpoint. It's just since it's asking for input. Now a good strategy here is to press Control C here. Control C in the terminal it usually just terminates the process, but in GDB stops the process at this point, which is asking for input. I see. We receive signal 2nd, and it is allowing to read the stack trace. type BT, and you get the stack trace. Here, this line should be like your user functions, like this is live main, this is the entry. This question mark here should be main. This one should be so whatever is checking the flag, decrypt flag. Actually, you see there's an address for them, except that address is not the load address. The address they loaded at, it's the address they are calling your thing. But a good pattern here, like to recognize that here is that like the last three hexadecimal digits of the address is going to be all the same regardless of randomization. B48 here. So let's try to find what B48 refers to in Ghidra. B48 here. It should be like right before calling this mystery function. Right before calling this. So the stack trace is showing this address because the main is currently in this function. So the main just pauses here, pauses this address so address and waits, and it's in this function right now. So it should be obvious like for now, because this the address here is just instead of 1, it is 8. So to compute the offset, we subtract. Do we want to subtract that by this address to kind of get the offset of the thing? Yeah, and give it a hex. Yeah, that will be the offset based from Ghidra, and you can store that in your variable. The variable is just internal to GDB. It's not anywhere else, so you can verify that I've set the offset variable to that, and that's the offset. And by the way, GDB can do math and arithmetic and other stuff like how Python does. So it's a very convenient feature here. So now we are going to break at the address we want to break it at, which is just before timing phase equal. Copy this into this. Plus now we add offset. And also the star here, you see, it's different from the previous one where we need to supply line numbers. If you want to break at an address, we need a star here. We need a star. And so here, this breakpoint should set successfully, and hopefully I didn't make this mistake here. Let's continue this thing with C. Continue. Let's just type some random string. Now, the GDB actually stops this address. It doesn't know where it is located, but we know it. It's before timing phase equal. Here, so a useful strategy here is that, in assembly, like how functions are called is that like it's moving RDI and RSI, which is 2 registers, and you show it here like RDI is the first one. The first argument is passing this register, and the second argument is being passed RSI register. And registers are like variables, and you could just print them in GDB. So here, let's see, you can print any register here. For example, arbitrary RAX, and we store some random hex value that's maybe some variable here, or maybe some address. But if you type RDI and RSI, they're actually the argument. It's just, since they are a string, they're just an address in memory. But how do I print them? Here I'm showing them in hex. If I print that in some alternate form, you see, the first argument is just RDI. I use, instead of P, I use X, which, this thing is that's like prints hex value and as a string. It's just a command that prints a string as a string form, and it is a string located at the address, which is random string. The second one, the compare against, I think it should be RSI. And yeah, this is the actual the right input to the program. And I can tell you that like if I actually input that, that will actually work. There are other ways to get this thing. Like just here we have a shortcut. We may want to know other ways too. Like for example here, and we could yeah. If the program doesn't pass anything to the register, like doesn't call any function, you can still get the variables, like these local variables. So how do you get those? So Ghidra is a bit complicated, but just find any line that refers to those variables and see the address. So compare against is being RBP minus 0x60. This RBP minus 0x30. RBP is a base pointer, which is a pointer to the top of the stack. Let me draw a stack here. In Intel, the stack goes downward, which is like for the main should be on the top. This function, whatever it is called, should be on the bottom. And above main is light C star main, and the stuff. This function, we are at here. So an RBP is always pointing to the top of the stack, and it has which also has the return address. If you know binary exploitation, all you have to do is usually an exploit would be to override this address and so that when it returns, it gets somewhere else where you want it to be. But here, for reversing, all you need to know that RBP points to the top of the stack. RBP minus 60 is somewhere like, for example, I'll just say RBP minus 0x60 somewhere here, and minus 0x30 is here. So you know where they're located. Here we are storing string on the stack, which is what you see it has stored string on the stack and not just on the heap. We did this thing. So here we have the input buffer here, and compare against here, compare against. So that when we do GDP like for the XS and this address, we'll be able to see this string. And if we do at this address, we'll be able to see the input. So that's how you print local variables without like debug information we had before. We'll go back to this and try this on our own. So let's type RBP minus 0x60. So here, that's the compare against, and 0x30 is random string as expected. And we can even print other variable types too, like not just strings, also print integers, and they're located at their address too. I won't go over all of them. Here, I will exit out of this. Yeah. So what's the main path? It's debug me and pasting this in. That's exactly the secret method. Yeah, I raised. It's basically like mind reading, except for the program, using it on the program. Okay, that's this. Yeah. So yeah, we finish this, and let's start with the next one. Not sure how you guys like constraint satisfaction. This one might seem a bit more like math, and not sure how you guys like this. This is definitely one type of challenge that CTFs may ask you, and it's quite useful to know it because I personally find it quite cool that you can use computers to solve constraints. I really like those reversing challenges. So yeah, so CTF challenge, yeah. So it's a bit theoretic, but for example, like if you have a binary that's of any sort, and there's always some way to translate this binary into a Boolean circuit. So, and any operation can be done that way. So For example, if the binary adds two numbers in binary, adding numbers can be represented by some like gates. If you took CC20, you know what those, how you can add those two numbers together to get, and you can add those two numbers using only like Boolean circuit. It's got lots of like XOR gates and all this stuff. So this just demonstrates that every operation in a binary can be translated into a Boolean circuit. And so, for example, this one, and reversing, it's kind of like a task when you have to solve the circuit, like kind of like solving equations, but with like Boolean variables. So my example is A and B XOR A XOR B is F. The only solution here will be both A and B are F, and that can be verified in truth table and all this stuff. And this is just demonstrating that, like, yeah, like how reversing like can be like, but for example, solving those, we as humans, we cannot really easily translate binary into like a executable binary into a Boolean circuit, but there are software that can help us do it and even solve tasks this way. So this leads us to Z3. Z3 is a solver, it's a constraint solver from Microsoft Research, and it does those tasks really well. You can install it with pip install Z3 solver. You don't have to compile from source or anything. It should be a very easy way to install it. If you haven't done so, just install it. I will also type it in the chat in case anyone wants to refer to this command. Okay, so I will give you a quick demo of what Z3 is like. I open this is a better Python from my Python. You just type the regular Python, it's okay. You don't need the I. It's just an enhanced version. I kind of liked it. So I'm going to import everything from Z3. In actual programs, you're probably not going to do that. You're going to just type Z3 dot something and just import Z3. But here it's more convenient on the line. Like you'll be able to refer to stuff without having to type Z3 dot. For example. So first, in Z3, the first thing you're going to see is, for example, variables and yeah. So we will first try an integer, which is an int, the Boolean in Z3. So let's declare. You need to first declare a variable. So like what variables you have in the equation, kind of thinking like that. It's gonna int a, and here you need to give it a name. It seems redundant that you need to type a here and a here, but the name in the string is what Z3 think it is. So this is what Python thinks it is. It's good practice to make them consistent, the same. Like so, they're both a. So yeah, if you run like Python, will evaluate that as a. Then it's just a variable a. It will use the Z3 name here. And for example, the power of Z3 is that like you can form expressions, like do expression overloading in Python. So for example, a plus 1, the result is not an integer, it's an object. It's a Z3 kind of like integer reference object. You can check it by checking the type of that. It's got arithmetic reference. So it's just an abstract object representing like the sum of these two, and you can just use the regular Python plus sign. You don't need to like add and a and one, all this like stuff. So Python is really great that it allows you to overload those operators. Do those, so without saying anything more, let's solve this simple. Let's do a simple math equation solving. Let's solve. Solve is something that helps you solve the equation. So it's a solve the constraints, and it actually gives you a very nice example. So if a is greater than 0, let's just do the example, less than 2, then it will just give the solution, print the solution as a is equal to 1, which is what we have. And you may wonder what will print if it's like if it cannot be satisfied when it's both greater than 0 and less than 0, what will happen in this case? It will say no solution. So as you expect, it won't print errors or anything. And you can add like an arbitrary number of constraints after this. So less than 2. This can be satisfied, but if I say it's equal to 2, yeah, it won't be able to do that. This is, yeah, it's specifically no solution. Yeah, you can add any number to the level. I will do so this simple equation, which is a squared is equal to 4. Double equal. Yeah, it will give you a solution. And note that here, like it doesn't give you all the solutions. So A can also be 2 and cos B -2, and Z3 doesn't do that. So as far as I know, like the only way to work around this is to add extra constraint. For example, I want A row to greater than 0. So now it prints the right one. And if you want the solution is less than 0, you do this. You add more constraints to it. So this thing is called a constraint, which is one extra requirement you're imposing on them. The constraints are connected using AND. So you have to satisfy all the constraints. So here is showing an example like to solve this system of equations. So we can see this. Yeah, maybe it's cut off. I'm not sure. X plus 2y is 167. Cx minus y is equal to 3c1. And this, you can just declare 2 variables here. And here, there's a shortcut of declaring 2 variables at once. You can declare them one by one in the previous method, but you can also do this, which is you connect x and y together. And here you get 2 variables here. And just a one liner that's shorter, not better or anything. Now we solve this x plus 2 times y. X minus y is equal to it's integers, yeah. So this time we're going to do real numbers since it doesn't have integer solutions. Here, see, it gives you a solution, and that is one. So basically, like math and boring. Well, we'll go with more. See how we can apply this to like make your own key generator, which is called can be used to crack software and other stuff. This is kind of interesting. Yeah, so to solve cracking. So here, download this one. So it's called activate.out. Just download this. Download this from the usual file repository, and it's a Pico CTF challenge, and it is solvable by Z3 very easily. I'll start opening this in Ghidra. Yeah, I already imported it, but you have to import the file yourself. So activate the out. Yeah. Oh, it actually has a main function because Pico CTF doesn't like strip all the symbols, so you actually have function names because it's kind of beginner friendly CTF. So here it asks you to activate using a product key, and it requires you to be 16 bytes, and actually it even need to be like a special some special characters that take valid call. I do it between 0 and 9 or between A and Z. So those are the only valid ones. There's a validate key function. Oh, it's a lot of constraints here. As you can see, the main constraint is the hints are we're going to put those constraints into D3 and solve it so that we can find the correct input that passes all the constraints, and stuff will cause you to print the flag. So yeah, I will log into my decoctf show. So let's just see what the binary is like. Go to activate somewhere. Wait. Oh, yeah, data file where is it located? It's here. Yeah. Activate the product key. So let's get a 16-byte key here. 16 bytes. So yeah, that should be it. I would say invalid product key. Yeah, it is still a random one. Yeah, that's a 16-byte product key. And just a flag there. So I can't. Obviously, you can't do that because the binary is 3-bit, and you need to go through the binary. That means now here so you actually have to solve those constraints and stuff. And let's see what the constraint is. So, and this will be the key, which is a string. And double click. So it checks the first character, the OR function. Basically, what the OR function does is maps each character to, it assigns each character a number, and it's just from 0 to 9. And this one 0 to 9, we'll just get the numerical value, which is to subtract that by the character with character 0, and it gets a value of the character of the digit. And if it's a letter, then it will subtract it from the capital A, not capital A, but yeah, subtract it from capital A and adds 10 to it, so it's to distinguish between letters and numbers. So the result will be that it will be something that looks like the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and A, B, C, D, E, F, G, H, I, J, K. Oh, I will not type all of them. So the first one is 0, and the 10th digit is A. So whether A gives you 10 because it is the 10th digit of this kind of real character set. 5 is just 5. That's basically what OR does. Here, going back. And here is also a mod. You should be able to guess what mod means. It's just modulo something. Yeah, it's running the modulo. Yeah, and this is a better mod because when it's less than 0, it's a corner case when you have to add by the second parameter, which is should be the thing to be modified. See what it is. It's 36. It's more 36, and it should be very clear that there's 26 letters and there's 10 digits, so it should be 36. So it's kind of like a base 36 encoded. See, think of that as that. And it checks that after adding the ordinal of like the first and second character, and when the module is 36, it should be 14. So the sum of first two characters is mod 4, it's 14 mod 36, and that's the first constraint we have. And there's more. There's more constraint. The second one is something very similar, and we're checking the third and fourth character. I think your first task is just to have to copy all those constraints out. It takes some time, but I already did that for you. I constructed a solve .py. See, the first thing is first, yeah. Solver is like the thing solved with it, except we are now adding constraints to the solver one by one. Like we are not just putting all on the same line. So that's just to make it more readable. A solver object keeps track of constraints. And here is a 12 constraints with almost 36. This second, third, minus 0 complicated constraint, and I encoded them in the format. And the part where I actually add the constraint is here. So iterates over all the constraints and decode it as to be a Z3 expression. And it requires that to be actually more 36. And I also added a constraint to make it between 0 and 36. This would be just my key generator. Those are the constraints, these 3 and these, which is the 12 constraint here. Eventually, I will check that it's satisfiable if it has a solution and get all its variable out, convert it to a character, which is in this table. Yeah. And with eventually it will print the flag, and I will demonstrate to you. Not the flag, but it's the activation key. Yeah, that's one of the possible keys, believe it or not. And we can run it on the binary to check it's actually the right one. It says product activated successfully and prints a flag. Yeah, constraint solving is way faster and with Z3. And my challenge here is to ask you whether you are able to generate a second key with the same constraint. And I will tell you that this is possible. It is possible to generate a second key because the constraints are not strict enough to. And I will also tell you that the first character can actually, there exists a key that has any arbitrary first character. For example, my key has start with D, but you can also construct a key that starts with A and starts with B, start with any letter or digit. Can you guys suggest a modification to my program so that I will be able to generate a more random keys? Because when I run every time, it always gives the same result. This should be a good question. So also, if you don't understand any part of it, maybe ask questions in the chat. And you want to participate and actually know what it is. So yeah. So can anyone give a suggestion of how you can generate any key other than this one? By modifying the program. So remember, what we learned is Z3 is entirely run by constraints. So if you change the constraints, if you add or remove constraints, it might give you a different result. So what will you change using what you know? Just wait for a sec. So a hint is that remember when we solved the equation, how we are able to get a second solution to the same equation, x squared is equal to 4, and Z3 just prints -2. But there's also another solution, which is x equal to 2. What did we do to make that happen? What did we do to the let's see if that's a listen. Yeah, I added x. Yeah, exactly. I added x is greater than 0 as an extra constraint to it. So now it can just default to -2. And you can actually do that with anything that's for example, you can also use x is not equal to 2. Also works. This one also works. I mean, sorry, that's x is not equal to -2. Yeah, that one. That one also works. actually it just need to be anything except like for the kind of like status quo what we already have. So to generate any key that is not this one, we can just what we'll do, like what do you think we'll do in this case? You want to generate some key that isn't this exactly this one. Just you can take any guess. Like even if you don't understand the program, give me a general gist of what you should be adding. Because currently the constraints are on letters. The letters which are like being encoded as numbers. So what is something you need to do to generate a different key here? So yeah, just what the constraint is there. Yeah, like adding, for example, requiring the first letter to be E. I will try that in my binary. So we'll add character bar. So the first character, and it has to be E. We say can I get E, which ordinal? The ordinal of E is 10. This is A 10 C D E. So it should be 15. Yeah, just run the constraint I added. Let's see what changes. 14. See here, now you have a key that starts with E. It's EOK for IO and stuff. Let's try that. See, it's also a correct key. So in reality, you can like generate like you can make the first thing like any like number or letter and still have it work. Here I will instead of making an E, I will, for example, to actually make a key generator, you probably want to be generating random keys because you don't want to have the same key to be used by two users. Since some servers, for example, for some software, they prevent the same key from being used twice. So that's why you need a key generator called keygen to generate a different product key for every user, so that like they don't get blacklisted for using the same compromised key all the time. They just found on the internet. So yeah, I will add a random. Random the next random range. Yeah. So I will let the first character be any random thing. Yes. Now it's A. It's yeah. It's giving O, and also no valid keys. I'm gonna try them one by one. So we have now built a functional key generator, keygen program, and it's going can crack like generate any random key sign. If you need more randomness, like now we generate only 36. There are also like other things like you probably be able to change another one. Like if you're lucky, I think we'll try to make the first character, and maybe it's just some trial and error and see if it works. If they have a solution, oh, this one doesn't work. I think there's one of the characters that isn't used. There's XP. Here's another character. Yeah, and we're giving them more randomness this way by setting the like 10th or the 12th character to also you can literally be anything. Yeah, so we've built a program that does key generator in sim program. Okay, now we're going over the limitation of this approach, like satisfiability and stuff. So first, just one problem that's still open computer science problem called the Boolean satisfiability problem, which asks if we're an efficient solution to reverse any Boolean circuit. So we need to find that is there an efficient algorithm which is ON, which like so its running time is kind of proportional to the size of the circuit, and that it determines the correct input. For most simple circuits, you can run it pretty efficiently, but there are always ones that are quite difficult to reverse. For example, we have like, what if the circuit implements MD5 hash? If you're able to like MD5, the program shouldn't be too long. If you can reverse the MD5 hash using time that's proportional to the size of the hash, then you are able to launch pre-image attacks and be able to like get passwords to every website where you have the hash, and that's a great security compromise. And actually, MD5 is already compromised, but pre-image attack, like getting the X from the hash, is still a hard thing to do. For now, we can only find it if X is in a well-known password or like combination of well-known things. So if you know, like, if you have been to the crypto workshop, you should know this MD5. Like, there's more about MD5. There, like NCO also have password cracking, but I digress. And this is generally it's going to be a hard task, and just say, and if you're able to solve this problem, find an efficient algorithm, you actually solve the P versus NP problem. Like, if you can run it in polynomial time, then you're demonstrating that P is same as NP. It's the same thing as saying that anything where you can try it by brute force, you don't have to try it by brute force anymore. You can just use a smart algorithm that does it faster. Yeah. So there are things, for example, if the binary is constructed in a way that checks your input, it hashes your input and checks if it's this long string, then there's like you're probably out of luck. So the CTF challenge just never asks you for that. When they ask you actually, when they actually hashes MD5, there must be some other way where you can get the input. You're never supposed to like reverse MD5 directly. So for most simple constraints, these three just solve it very easily. Don't expect that to like solve every single case in like every single binary in the world in an efficient amount of time. And okay, let's go to the next one. So now we are going to discuss on like see some anti-reverse engineering strategies. So this is what probably software companies will employ to make the life of the reverse engineer harder. And some CTFs also do this to, but the CTFs usually use simple methods. And see, here's the background. You can see it's an internal security violation. And there's a poem saying the tree of evil bears bitter fruit. And at the bottom, it says trashing program disk. And it's a very old, I think, version of some Microsoft software. When you try to run a debugger on it, it detects it and try to scare you by saying that it's going to format your drive. In reality, it will not be doing that. It just warns you, like, wants you to go away, like, not try to like reverse engineer its software, so that so you don't crack it and everything. So here, probably the most simple ways of doing this is through the two functions time and rand. Those two are pseudo-random or pseudo number generator, and it requires it's a built-in function to the C library. Pretty useful tool. In C, you can just type srand and make it seeded, and it will start generating random numbers. But the one flaw of that is that, like, if you don't seed it, or if you seed it to anything, if you seed it to the same seed every time, or like if the seed is same for any two times, the random sequence will be the same. Because as the program only knows deterministic stuff, you will need to find a good random source program like dev random, I believe it is. For example, there's a better random source you can use your seed generator step urandom. Let's type to find the first character. Yeah, and we give you random bytes every time you run it. That's a much better random number generator here, and you can use that as a seed. Poorly written program, like those program, a lot of programs actually do it the incorrect way, which is trying to see the random number generator using time, like using the system type. So to demonstrate the system time, so I'll run dates that is this number here represents it's called the Unix epoch. It's a time since a fixed time, such as like since 1970, like January 1st. I think that's when the Unix machine was born. And then Linux just inherited this thing. Every second, this kind of clock-like thing is going to be incremented by one. And the clock. So this number is returned on a library called to time. It's not time t, yeah. It's this library called. If you run time now, it will return this number, and every second is incremented to one. It's changing, so it seems that if you feed it by the system time, every time you start it, it's going to be generating a new random sequence. But the problem is, especially if you're using it for security, that's a kind of bad practice. First, the system time is in like the time only returns the time as only as precise as 1 second. It doesn't go to nanoseconds or microseconds. So every process that's spawning on the same second means they will generate the same number, the same deterministic number, and it's no longer random. This can also be exploited by hackers to like kind of cheat on games and stuff. So as we'll see in the next slide. So here it will be a simple dice game, and so I want you all to download the binary and be on a Linux machine, check if it works or not. And yeah, just download this binary and run this, and see if you can guess correctly the sum of 3 dice roll for 16 consecutive rounds. So I will demonstrate here. Game. Yeah, you run it by /game, and yeah, it's a game of die, and give a guess. My best guess will be 8 because the sum of 3 dice roll is the most likely ones. This is 15 and it kicks me out. You have to win 16 rounds in order to actually get the flag. Relying on purely on luck is not really going to help you. Oh, I guess you get the first one right. I have to do this 15 more times. So it's 8 again. And yeah, we kicked out. So how do you actually hack this game? So first, I will demonstrate that the 2 games launched in the same second will have this same role. Restart. Yeah, I'm not sure if it works, but because it kind of oh, it works. Yeah. So see, they are all launched on the same second. And this one, the first row is 13, and the 3 dice look exactly the same as these 3 dice. Yeah, and they're both 13, and I just copy the sum here to here. So by this, you can actually technically launch the same game, 16 instances of the same game on 16 terminal windows. But that is kind of quite difficult. You can try scripting that out. I'm not going to go that way. It's kind of brute force. There's a better way to do it. So So first, let's try opening the in Ghidra to see how the random numbers are actually generated. So there should be a way for us to tell like every second, like what should be the sequence that gets generated to be predict, because the program uses a deterministic algorithm. It's not exactly the rand we described before, but it's a similar random number generator, and everything just depends on the current time. So let's open this. Okay. Analyze this. Okay. So you go to main. Yeah, those are the functions. It's a bit difficult here, so there's a lot of functions here. This one, yeah, it's loading the flag. Yeah, so here, see, it's running time, so I'm now on a null pointer, and it's initializing that to this. This is actually the backend, the current state of the internal like random number generator. This called state, and this in run cycles to the runs one iteration of the random number generator and multiply it by a number plus one. This thing is called the linear congruential generator, which LCG. It's a type of random number generator that RNG generates random number on every iteration in a deterministic way. So once you know the time, you technically make a script that does this. And yeah, first it will do it 256 times, and just to like warm up the generator. But here, this is actually what the game stuff. So yeah, I will ask for a guess, and you input something. I roll the dice, roll the yeah, I will roll the die and do some fancy printing and stuff. Basically, it simply generates a random number. This is a actually rand int. It's a rand int function, and it is generating the next random number with the upper bound of specified by the parameter. So every round is running just 10 times, and it's only going to pick the result of the last iteration. Quite complicated process, but all of them can be emulated using a simple Python script. Because open solve the keys solve this way. I built a solve script for it, and it does this automatically. Or emulating the same function as before. And you see. And also, yeah, automation. Yeah, this is exactly like automate the same task is doing. Like, but make sure you don't actually like when you actual CDF. I'm not sure what you mean automation. Just don't run automated tools against the target. So because when you 16 rounds, the probability is going to be pretty small, and you can't get it a brute force. You can automate, maybe to automate locally is okay, but don't try to brute force the target. And this solver, and here, see, the prints a bunch of numbers, and you see, if you run in the same second, it still print the same sequence. It's emulating what the game is doing. So this kind of cheating tool, I'll use this cheating tool to and like run this before the game starts. Semicolon that's when it runs game immediately after the scene. And now let's try 15. It works. And next one. If you just use a copy all the time, it's gonna be a bit boring if I just type it one by one. But you can pipe that to the game to make it even more automated. It will automatically send the output to the game. Maybe there's no on the same different seconds. Yeah, sometimes it will not work because it's running at the exact boundary of a second, and see, now it's rolling a die all the time, and eventually it will print a flag afterwards. While we do that, I will send the solver into the chat, and I will give you one challenge, is to use the solve script, attack my server, which is like I set up the same instance of it while running on my own machine. So don't try to like use automated tool because it can ruin the experience for everyone. Because if one person tries to DOS my machine, it's a virtual machine, so it's rate limited and everything. So other people won't be able to do it. It's giving you the flag. Flag. Wait, it's not the actual flag. So like, yeah. Hopefully nobody will see the flag. Yeah, should be good. So, what I want to do is like you are going to attack my instance of the machine and get the flag running on my end, and yeah. So I will send the script into the chat, and okay, yeah. So you guys see this command, and this not sure if it's cut off, but it should be nc net, then we stand for netcat. This thing, if you have done the CTF before, you will know what nc means. You usually need to connect to this target, and it should present you with a dice game if it's still running. Yeah, it's a game of die. But this is connected to my own local machine. This one is a public URL, and you can just go anywhere, and you'll be able to connect to my own machine this way. And so if you're running on any Linux VM, I'm not sure, maybe there's a Windows version of Netcat, but if you're on Linux, there should be a command which nc, if it tells you command not found, maybe search on the web for your distro, because at least it's by default installed on Ubuntu. Maybe on Arch Linux you do have to install it, but it should be pretty easy. Just search for netcat, and it should be something like be able to download it. Yeah, the command is just nc, and I think. And what I'm asking you to do, so the challenge is trying to get the flag on your end and send it to me privately via chat, so that I know that you get the flag. Using the same typing strategy I use. And I will send over the solve script in the Zoom chat right now. So you can put files here. Wait, can you guys send files over this? No, man, I will just try to upload the file into the Google Drive, same folder as before. Wait a second, I'm gonna upload the script so you guys can use it. Wait, give me a sec. Yeah, it's uploaded. So just check the workshop files for the if you refresh it, you should see the solver.py here, and you can download it from there. And maybe try piping that into this netcat prompt and see if you can hack my instance. I'll be there monitoring, so if you come up with any problem or so, and I can check who actually logged into it. Yeah, yeah, connection. Yeah. For now, only me connected to it. Oh, yeah. When you connect, the number should pop up just so you can check. Okay. And here's the command in case you want to reference it. So if anyone has a Linux machine, maybe type this into your command and tell me if there's any problems with that. Oh, I think someone connected to it. So great. So someone actually managed to connect to it. So once you get the flag, message me. Also, sometimes can be quite difficult to like navigate between virtual and machine and like real machine to get files into it and out of it. Uh, but yeah. Another way is to manually type by going into the machine and out, and like maybe like make a side by side window. Like one is running the solve script and one is this this command and just types it in from the other window over there. Yeah. Another person's connecting. Yeah, maybe the same person. I see those people connecting. Also, uh, uh, sometimes it can be actually a bit annoying, you know, because the time doesn't match exactly. So if you try enough time and maybe modify your script to account for delays, like like add time by one or subtract by one until it worked. And yeah, and also private message with the flag if you get it. Right? What does it mean? Existent or nine left? Maybe it's I got screwed up. You just screw up in the middle. So yeah, like I don't see a lot of people. Like maybe not everyone's doing this, but for now, maybe we'll move on to the later one. You can still try get the flag maybe by the end of this workshop, and I will also need more time later on. But now we'll move on to like other things. You can still like run it. It's still up. It's just like I will like close this console for now, and yeah, so that like most of you guys we can like just continue the workshop. And here go to the next. So here we'll talk about obfuscation. And this is a strategy some like miners, some some CTF challenges do. Is that it's quite advanced strategies that like this obfuscation is like more than just like stripping the symbols and stuff. As making the code even more unreadable, even as like even for people who are good at assembly, it's going to be very difficult to read. For example, one of things you can do is use a packer, a UPX. It's called the ultimate packer for executables, and you can actually use that packer to wait, someone raise a hand. Because is it Mate? Yeah. Not sure if we're doing that, but I'll just so okay, there's a very easy way to yeah. Let's see. It's okay. It's okay. Hacker render and like you can easily reverse that by like having UPX -D. I didn't realize in Stone CTF that you can actually reverse and unpack something. It's pretty interesting, and there's also CTF challenges to switch between like 32-bit and 64-bit by like changing some like using some magic in assembly. And also, there's CTFs that like if you use CTF, like they make the binary like kind of like broken. It's almost like forensic challenge when you have a broken image and you have to repair it. So this is for binaries, and it runs fine, but it's a pain for debuggers and things like Ghidra, and you have to manually map memory. Since this is the intro level workshop, it's kind of out of scope, so we'll not have any examples with that. But this one we do have one. So it's an anti-debugging strategy here. So here it is anti-debugging. It is checking the if it is checking like the p-tracing. The trick is p-trace is a function that like it is kind of system call you can use to debug programs. But using p-trace, you can also achieve anti-debugging. Since there's a very interesting property is that a single process can't be debugged by two processes at the same time. And this is true for anything, like even if you're running as root, so the second time, if it's already being debugged and it's trying to debug itself again, like it will like the p-trace call at least itself will end with will return -1 and say operation not permitted. And you can actually exploit this fact to say that, oh, now I detected a debugger is running on me. So the binary is just going to say, I'm going to exit because I don't want to get my memory being hacked by the debugger and leaked by the debugger. Some commercial software will employ this strategy. And this strategy is quite really simple and it's an easy way to like circumvent it. Because all you have to do is patch this code out. So it should be easy to like, for example, if you have the source code, you can just comment these two lines out. But in reality, you don't have the source code. You can try decompiling it and recompiling it, but that may not work. Decompilation can actually lose some information in that. And it's very hard. So the easiest way to deal with this is just to patch this out with replacing the assembly instruction that does this with NOPs. NOP is an assembly instruction that has a bytecode of OT code of 0x90. I think Intel like x86. But this is an instruction that does nothing. So for example, if this is doing a call trace and you replace that with not, and this line will be gone. And like commenting our stuff in assembly. Yeah. We'll go to I will try an example out. So download the anti-debug out and anti-debug C. Yeah, this time you have a source code and it's actually recompiling about I want you to do is I want you to like try doing it without like recompiling. Also, recompiling requires you to have a compiler. So if you don't have a compiler, the only thing you can do is to patch it out. So what I mean by patching is to replace, trying to use a hex editor, which is editing the binary code and replacing segments in the code with not. And this should be more clear when I actually show it myself. Okay. So yeah, I will open up the source. See, this one, your goal is to like get you here, run the code here, the mission accomplished, and here it is running the no debug function, and in the no debug, it is forbidding you to like performing p-trace by so let's see what happens when it's running normally without the debugger. It passes the debug check and it goes to else clause and says, "Muhaha, we're not going to get me this time." So yeah, we like failed to get to this part because this variable is 0 and this kind of dead code, it won't happen unless you attach a debugger and change check to 2 here. So yeah, so let's try debugger then. Anti-debug. Let's try anti-debug. Run this. And here say p-trace operation not permitted, and don't try to apply debugger and exit it with code 1. So ends with here like exit failure. Detects that the debugger is running and refuses to debug it. So we'll have to patch this up. So actually there is another way to circumvent this using a debugger. It's like setting breakpoints and the smart way to like actually bypass this. The easiest way for me still like is to just run the hex like edit its like the binary code directly using hex edit. So in Ubuntu, I don't think this is installed by default. You may have to run like sudo apt-get install hex edit to get this if you want to run it on your own. But I have it already installed. So so here is the hex editor. So you can change anything by typing in anything and replacing that with any code. For example, like I want to modify this to like some random ones. And you can change anything here. And you can also modify the text. It's a very powerful thing to edit binaries this way, but we're not going to edit it this way. So I'm just going to press Control C, which discards the changes. I don't want to change it this way, so Control C. Now it's out. Let's restart it, and we're going to first know where to patch. Where is this thing located? So if you have a source code, there's actually an easier way. Assuming you don't have the source code, you have to go to Ghidra and find the address again. This time, there's a correspondence between where the file is located and the address. I'll open this. Okay. So here we're gonna see this line and where it is actually trying to reject debuggers, and the comment that also rather than commenting this entire function out, it's way easier just to go to main. Usually just a function that just do anti-debugging stuff. So here, this thing, these OP codes like E8, 93, FF, these are the code that's responsible for calling this no debug function. So if we can replace these with knobs, right? If we can like replace get it out and change it to knob, the code will just skip over it and allow the debugger to change the and the other stuff. So it requires these to be changed to or 90. If we hex, of course, 90. So now we have the address. So I will copy this address out and put in. Yeah. So this address is not directly. If we just try to go to this address, that will not work. Most likely, it's an invalid position because obviously Ghidra is adding this one here. So there's an offset. So this is where the Ghidra shows where the program is located in memory. What we want is where it's located in the file. Ghidra has a tool to view it. It's called display memory map. Open this up, and it shows you the correspondence. Yeah, byte source is what we're interested in. So generally, actually, it gives you a much better summary. It's image based. I think image based. This is the offset. This is added to every location. This is the location in the file, which we'll put in the hex editor. This is like the 0 is the first byte of the file, which is the ELF header. It should start with ELF for Linux binaries, and add it to this, and it becomes this. So yeah. So all you need to do is subtract that by like to do some subtraction. So it should be the last 3 digits, 7A2. Now let's try that. Now we're going to 7A2 in this. The bytes are the same, the E893 FFFFF. Just verify that, look at the correct place. Yeah, so it is correct. There's a call instruction here. So we're going to change this all to knobs. The 90, which means knobs and doesn't do anything. And you can add any numbers with them. We'll still work fine. Now Control X, so it will save it. Yes, and now it is saved. And now it's passed, so you can try running that again, and it worked. And yeah, you run it GDB, of course, to check that it actually works. Yeah, it actually allows you to debug this time. It's just you need to set breakpoints at like certain locations and change it. Okay. So let's break it as we want check to be false. It should be true, so we'll break it 34, which is here. And there's actually address for it in GDB. And GDB infers it for me. So now run this. Now it's like this, so let's check is it 1. Continue. we make this binary mission accomplished, which is what we wanted to do. And actually, let you guys see where the knobs are. I will run obj dump and actually, so you guys get a better view of what this actually. This thing, like in Ghidra, it used to be that there's a function call here, no debug, and here it's all replaced with knobs, with 5 knobs. So knobs is a very powerful instruction here because it allows us to like change instructions. But I will propose another way, and let you guys think whether that will make the binary run or not. So I see that why replacing with knob when you can just delete those bytes? Like if I deleted all those knobs, and so that this move instruction goes here and has the same address as this first knob instruction, would the binary still run in that case? So what do you guys think? Maybe type in the chat what do you think will happen? Would the binary even like run, or will its behavior change in any way? Yeah, it will. When you say that it will run, can you say why? Why do you think will run? Because I know that's kind of an intuitive thing that like in C, if you remove a line of code, it's still going to compile and run correctly. But note that one of the job of the compiler is that, and also assemblers actually also do that, is that it makes sure that like the addresses are correct. In other words, maybe I think an example here. So for example, I would go with an assembly-like language at least to get a sense of like what most compilers does. Just go with C, like we can make it easier to understand. For example, I have like print hello world, which is a pseudocode, not any specific language. But for example, we have a function which add 1 and it returns x plus 1, for example here, and add 1. We can make a very okay, print add 1 of 3. Okay, the output of the program should be like hello world and 4. So yeah, how is that compiled in binary? A possible way as this compile is that first binary I was as I said before, every line has an address. Every instruction has an address. For example, just we'll start with 000, and this is be some code for like there's probably not instructions for print in assembly, but it's just do for demonstration purposes. Like there will be a print hello world instruction, 001. Actually, there should be much greater. An instruction should be 1 byte. I will also do this just for demonstration. So this will probably call add 1 x add 1. Maybe there's access to it's probably more instruction, but this is just demo and print like a result. The result could be like any type of return from call. And then after this, it hasn't ended yet because we have a function here, and you see we have which is here. Just make a comment here. This is going to add 1, but in binary, this line doesn't exist. And immediately following it, should be maybe some exit instructions here, like exit program, and add 1 should be at 4. And immediately after this function, there will be the next function. Wait, are you guys seeing my screen? Oh, yes. Immediately after, oh yeah, the answer is correct. Yeah. So basically, input plus 1. Like if you just remove this line, then the result will be I get rid of this. This become address 1. No, the address change because the address always work like the first byte, the second byte, third byte in the file. So now the call add and now everything is missed. It's just more functions. Another thing that calls add one and different addresses, and this is technically hard coded to 003. So now you're 004. You're now calling some like bad invalid addresses here. So that's what will happen. So by replacing that with not, you now mitigated that issue. Yeah. Now, goes. So yeah. So we'll just now go to our final one, which is not malware. It is from the CSOS qualification round, a reversing challenge there, and also download the flag.txt associated with it because you need flagging this txt in the same directory to run it. And I will give you an example of how this thing will run. Yeah, I would. This is in my virtual machine. Restricting connections. Okay, so look up. Which one? No. Yeah, it actually was a credit card number. Then just type some random numbers. It's not even going to say that you're wrong, but you can see the return value is 1. So that means something is wrong here. You can try with maybe different numbers. And it doesn't seem that it's doing anything. So let's open it up in Ghidra and see what is happening what's happening behind this thing. Import. So yeah, it's going to go to the first thing, go to the entry. Actually, go to the main function. It's kind of very long, has a lot of local variable. Those shouldn't be variable. There should just be one big buffer. Ghidra sometimes break it up. So okay. So first ask what is the credit card number or safekeeping, and it can't be too long, and otherwise it will just exit. So first, it runs 16 to the 1/2 power, which is just square root of 16, and it will just print 4. Maybe make a note here, and this will be 3. And it's just an extra layer of obfuscation to kind of prank to make it like more obfuscated. And then yeah, this is the input buffer again. So it doesn't just send the input with everything. Oh, it copies the input buffer and actually compares the copy. And it seems that it's comparing this with another thing, and it has to be equal to EPAN. But here, this thing. So in Java, this actually appends this number to the end of this. But here in C, that's one not what you do. You see a string is nothing more than the address of where it's located. So So if I double click this, I see there's more options you can here. So it's adding this number to like this address, which means that 3 times 9 is 27, and it will go all the way down and it will go to SoftBank. So well, actually, it's not UBank and it's SoftBank. It's another fancy referring to this thing. Yeah, and so and oh, now here is open get out. So this is a hint you can use, and we can use to help us reverse this binary. So let's try this. SoftBank. Yeah, let's just get out means everything, and other ones won't work. It was so it needs an extra colon, and as we see before, and there's still more checks. That's not the end of everything. But what I will tell you that is this will require some debugging. So if you can try running on your own and see what you can get out of here. And yeah, it has all these checks. So these are afterwards, and subtracting this by whenever you see 0x30, you should immediately tell you that this is probably dealing with numbers. So this is the character representation of 0, and this gets a numerical value, a value of digit. This digit is 5f, and this is actually part of one of a bigger buffer, which is part of the input buffer. It can recognize as a local variable. There should be an indexing on the. So this should be the character that's after the colon, the 3 characters, and later I guess there is a function here. That's kind of like a magic thing. I will tell you this will be very easy with a debugger hand. So let's try run GDB on this. See what will happen. It might be a bit surprising to you, but I've talked about this before. How this, and you see it exited with code 01. With very careful attention to what this is actually doing, there's a function here. This calls these 3 functions. One of them is anti-VM. I'm not sure why this can actually run in a virtual machine, but this doesn't get detected. But the other ones definitely do. Like, for example, this thing is checking for like preloaders, and this is one way you can debug a program. The other ones, yeah, ptrace trace me line. This binary is also anti-debugging, so you have to patch out the first function in order to like do some patching. Then hex edits anti-debug. Now, so let's do some. So figure out the address is should be 57. Now we 1, 2, 3, 7. Here we go. Let's patch this out. Check if this works. Oh, okay. So now we should be able to run GDB on it. See, it will be able to like and so we need to set a breakpoint here to get whether this is doing here. So it is printing some like magical kind of string, the local B6. So it is setting this one too. it is, I will tell you that this is computing a number that's kind of based, or it is computing kind of like some weird sum and stuff. Uh, all it does is like local 88. This one is the thing you have to like make it. You make the spin equal to. Yeah. So eventually, actually, you see all this stuff is checking this really the same buffer, and we just have to obtain the content of this buffer using the same strategy. With first figure out the address. Yeah. There's a useful way is that when you don't know what RVP plus something is, like where is local variable located, just find an like instruction, right click instruction info, and they will tell you it's RVP minus 0x80. So yeah. So first we set a breakpoint somewhere just after, just before this 4DA. We have to first get addresses. This time in this machine, usually we in Linux you get like a 0x5, a bunch of fives. So yeah, that's the offset. You should now be able to set breakpoints. Break at, you wanted to break at just before the comparison. 48. So here, I will try to print the value of, what is that again? Minus 0x80. P minus 43 minus 0x80. So print the string. Yeah, it's a series of numbers, and that's what you have. These numbers actually depend on what you input. I did SoftBank, like the colon 1, 2, 3. So if the first 3 digits are this, and this will be your valid thing to follow. And yeah, I think yeah, and also at the end, you need to like, there's also some checks at the end to make sure that you need something for like after SoftBank there's an end here. Yeah, if you remember it right, it is usually this number and oh yeah, and that will be the flag. It's just the thing you get in the debugger, 1, 2, 3, and those things, and the colon end, and that's a fake flag. It's not the real flag. It's a flag that TXT I just put in. But it demonstrates that you can find a digit for everything. So this can actually be done using other by using other numbers. That's not the only credit card we accept. You can use the same GDB strategy to get a second one. So as that, I would let that as like a thing you can do on your own. Maybe find another set of numbers other than 1, 2, 3. But also and this part of the number is going to be different. The second part, maybe find another credit card that's this binary accept. Yeah. So this is the final binary. Not sure if anyone has solved the dice challenge and got the flag for that. It seems like there's someone trying like just searching total connections. Yeah, it still works. This is it because the timing isn't really accurate? Like the time should be quite accurate, but maybe like add a time, like if there's network delays, you may want to account for that. Another thing is that in the Python script I provided to you, you can run the same function with different speeds, and maybe try one of them until like the latency gets up. Yeah, but that's okay. So I think our workshop will end with like question. Yeah, so that's all the end of the workshop. So if you have any questions, maybe type in the chat and I will answer it to the best of my ability. Yeah. And the dice challenge is still up, so maybe, yeah, it's just to be able to use voice. Maybe also tell you like system, maybe how you actually get stuck. Does the Python script work? Does it fail when you run it? Like not like the script doesn't output the right combination because I tried it and sometimes it doesn't work. You may have actually have to adjust. Like in the Python script, I can show you like you, uh, the dice challenge. Dice, yeah. So you can, for example, if the time is kind of off, you can always like I did this, so it prints the rows for that you need for like kind of like 4 seconds behind and 4 seconds after. So here, well, it's always 7 for 4 seconds behind, 9 this time, 14, 10, and 10 should be the exact ideal one, but it doesn't always the case. And the dice game prints you the first roll when the thing failed. So you may see like you can use it to debug like are you behind or ahead, but sometimes just like different time may start with the same number, so it's a bit difficult. I can always change the challenge to like print the current time. What is it? What is it again? Mathematics? Yeah, we just okay. Okay. So maybe try that again. Also another thing is to just run time +1 and see if this works. Because usually just a delay, and sometimes +1 works. Yeah, I'm just getting like you like ready for those CTF challenges where you have to connect with a netcat and get a flag over it. It's going to like give you a feel of what the result looks like. I will try to do it on my own side to see if there's any problem. Let's see. Oh, I think it's succeeding on my end though. Like when the pipe users command to pipe it, it's getting to it. So like see it's so maybe you can try that and I did pipe the script to that. Yeah, just so you can see the flag. It won't like show the afterward, show the end. Oh, yeah, Chris. Oh yeah, Chris like